In this video, we're going to learn how to evaluate the end behavior, or in other words, find the limits at infinity for rational functions. And I have three different problems we're going to do, and I'm going to show you two methods for doing these problems. For the first problem, I want you to determine what f of x approaches as x approaches negative infinity. All right, and the function we're working with is 3x to the fourth minus 7x squared minus 1 all over x to the fourth minus 2x cubed plus 3. So the way we write that mathematically is find the limit as x approaches negative infinity of 3x to the fourth minus 7x squared minus 1 all over x to the fourth minus 2x cubed plus 3. All right, so the first technique is to determine the highest powered term in the denominator. And we're going to, in essence, divide every term in the function by that power. So I'll show you what I mean here. So the largest term is x to the fourth. So we want to divide every term in the whole problem by x to the fourth. Or another way to say that is I want to multiply the denominator by 1 over x to the fourth, and I'm going to have to multiply the numerator by 1 over x to the fourth. And that is because we can't just multiply the denominator by 1 over x to the fourth, because that would change the problem. But by multiplying by this, 1 over x to the fourth divided by 1 over x to the fourth, we're in essence multiplying by 1. So I'm going to go ahead and multiply this out, and I have to distribute the 1 over x to the fourth with all of the terms in the numerator and all of the terms in the denominator. So I'm going to get the limit as x approaches negative infinity of 3x to the fourth over x to the fourth minus 7x squared over x to the fourth minus 1 over x to the fourth, and that's all over x to the fourth over x to the fourth minus 2x cubed over x to the fourth plus 3 over x to the fourth. And now when I simplify, I'm going to have, we haven't taken the limit yet, have we? So I have to keep this limit here. I'm going to have 3 in that first term minus 7 over x squared minus 1 over x to the fourth all over x to the fourth over x to the fourth is just 1 minus 2 over x plus 3 over x to the fourth. All right, so we're ready to take the limit now as x approaches negative infinity. And so if I have negative infinity and I plug it in for x, and we can't actually plug negative infinity in, but what we're thinking about is plugging in very, very large negative numbers, right? And so if I plug in some very, very large negative numbers, this is going to become increasingly large. I mean, thinking 1 billion, 1 trillion, those types of things. And 7 over those very large numbers is just going to go to 0, isn't it? And if you need to prove that to yourself, put some very large numbers into your calculator for x and see what happens. This number, 7 over x squared, gets very, very small and eventually goes to 0. All right? And the same thing is going to happen with the next term. That's going to go to 0. The same thing is going to happen with this term. It's going to go to 0, and then this term is also going to go to 0. So all you're left with then is the limit as x approaches negative infinity of 3 over 1, which is just 3. The other way to tackle this problem is to think about this function, and if we were to plug in increasingly larger values of x, then x to the fourth is going to be a huge number, right? So if we plugged in let's say 1 million, when we took 1 million to the fourth, it's going to be an extremely large number. And it doesn't matter if we subtract minus 7 times that same number squared. That minus 7 times that same number squared is not going to make a dent in the 1 million to the fourth power, is it? So that's not going to make a dent. So this one really is negligible. It doesn't make a difference, and neither does the 1, does it? In the bottom, in the denominator, the same thing goes. If we were to plug in 1 million for x, and I'm just using 1 million because that's a large number, but we're talking about even larger numbers. If I plug those in and I take it to the fourth power, then it doesn't matter that we subtract out negative 2 times x cubed. You're not going to get a number that we even understand. It's still going to be very large. So this is really negligible, and so is the 3. So really, the only thing that we need to consider is the largest term in the numerator and the denominator. So this is a pretty convenient method. We can take the limit as x approaches negative infinity of 3x to the fourth minus 7x squared minus 1 all over x to the fourth minus 2x cubed plus 3. And for very, very large values of x, this is basically the same as the limit as x approaches negative infinity of 3x to the fourth over x to the fourth, right? Those other terms really just go away when we're talking about very large numbers. They are not important, or they're negligible. They make a negligible difference in in the numerator and the denominator. So now we can simplify this, so we get the limit as x approaches negative infinity of just 3, because x to the fourths cancel, don't they? And remember, the limit of any constant, it doesn't matter what we're approaching, is always just that constant. So we get the answer 3. So that was the second way of doing this problem. And you can do the problems either of those ways. You can choose which way you prefer. I want to take a second and look at what we just found. Here we have the graph of the function that we just found the limit of. And we took the limit as x approaches negative infinity, and we got the answer 3. And so if you look at this graph, you can see as x approaches negative infinity, as we go off in that direction, and you could even zoom out even further, you can see that this graph is approaching the line y equals 3, isn't it? That's the line y equals 3. If you trace it all the way over here, you'll see it crosses at 3. And it never crosses that line. And so what we can say is that y equals 3 is a horizontal asymptote. Y equals 3 is a horizontal asymptote. All right. All right, for the second problem, I want you to find the limit as x approaches negative infinity of 6x to the fifth minus 2 all over 3x squared plus x to the ninth. So you can choose which method you prefer to use, but I'm going to go ahead and do this one again with the first method. So if you'd like to follow along, you can. So what I'm looking for again in the denominator is the largest term. And so this is x to the ninth. And it's not always going to be in front, is it? So don't always just take the first term in the denominator. You want to look for the largest one. And by the way, if it had like a 2 in front of it, when I'm saying the largest term, you just have to really worry about the variable. You don't have to worry about the coefficient. So in this case, you would not divide everything through by 2x to the ninth. You're just dividing through by x to the ninth. So let's go ahead and do that. So I'm going to multiply everything by 1 over x to the ninth in the denominator, and again, everything by 1 over x to the ninth in the numerator. So I get the limit as x approaches negative infinity of 6x to the fifth over x to the ninth minus 2 over x to the ninth, and then 3x squared over x to the ninth plus x to the ninth over x to the ninth. And we're not doing any magic tricks here. All we're doing is manipulating the function a little bit so that it is easier for us to look at in terms of the limits as x approaches infinity or negative infinity. And again, it's completely legal because this is in essence multiplying by 1, isn't it? So now we get the limit as x approaches negative infinity of 6 over x to the 4th minus 2 over x to the 9th all over 3 over x to the 7th plus 1. All right, so now as we get very, very large negative values, these terms are all going to go to 0, aren't they? And again, you can prove this to yourself if you need to plug in some large values for x and see what happens to this term right here. You'll see it gets smaller and smaller. It's going to go to 0. And then this one will also go to 0, and the only one that doesn't go to 0 is the 1. So what we get is the limit as x approaches negative infinity of 0 over 1 is just 0, isn't it? So again, this tells us that we have a horizontal asymptote at y equals 0. So again, you can see that when we take the limit as x approaches negative infinity, that this graph is getting infinitely close to y equals 0. In fact, on this picture, it looks like it's touching y equals 0, but if you were to zoom in, you would see that it's actually just getting very close to y equals 0. So for this final problem, we're going to take the limit as x approaches negative infinity of 7x squared minus 2x over 15x plus 5. And I'm going to go ahead and use the second method on this one just to give you some practice. So we know that when we take the limit as x approaches a very large negative number or positive number for that matter, that the largest terms in the numerator and the denominator are the only ones that matter. The others become negligible. So negative 2x is going to become negligible, and so is 5, isn't it? So all we have left is 7x squared over 15x. And then that is equivalent to the limit as x approaches negative infinity, this should have had an equal sign, of 7x over 15. All right, so now when we take very large values, large negative values of x, so as we go off to negative infinity, this is going to go off to negative infinity, and then the 15 won't really matter, will it? Because negative infinity divided by 15 is still negative infinity. So our answer here is negative infinity. This means that the graph veers off to negative infinity as x goes to negative infinity, and there's no horizontal asymptote. And again, just to give ourselves some confirmation about what we just found, we can see that as x goes to negative infinity, as we go off in this direction, the graph is actually going in an infinite negative direction, so it's also going to negative infinity.